Let's continue with our lecture on potential topics. So I hope all of you have tried to understand the videos on lecture 8. Okay, particularly on the topics of work, work in electric field, and then the topics of potential, and also on the concept of potential difference. So those are the topics that have been we have learned about these topics in lecture 8 throughout, using the videos that have been posted on Tuesday. Yeah. So let us continue with exercises related to these topics of potential. So I believe that we have done this example on Tuesday's class. Okay, before that, I did receive a message from one of your classmates regarding mistake that I've done related to this example. Yeah, this example, in the solution, I make a mistake. Yeah, I made a mistake in which the point P is having some error. Yeah, supposedly it should be -1, 1, and 2. But in my solution, I put it as a +1, -1, or 2, if not mistaken. So please correct that for me. Yeah. So that's my mistake. Sorry for that. But the idea, the concept should be the same. Yeah. Okay, so let's have a look at this example, a new example. This is a sample of, I'm not sure, this is a test question of an exam questions, yeah, a few years back. Okay, so we are given this example, whereas we are having two long wires, we are said to be parallel wires, and the space between these two wires is 2s, is given here. Okay, is given here. We have a 2s spacing between the wires. Okay, as stated here. Apart from two wire transmission line with densities of positive, negative rho L. Okay, we have positive, negative rho L and positive rho L here as the wires with the charge density amount. Yeah. So basically it should be in coulombs per meter, yeah, because it's in a wire transmission line. So rho L should be in the units of coulombs per meter. And it is stated here that the field that we are dealing with in this example is a static case, okay, static case, and the medium is a free space, yeah. And then we are saying that we are given that the origin of the coordinates here is given or is taken as the reference for potential. So then determine the potential difference between point P and the origin in terms of R1 and R2, which means that we need to find a potential difference between 2 points, which are the point of P and the origin. Okay, so need to find the potential difference. Yeah. Okay, so basically this is in order to solve for these questions, it is related to what we have learned previously in lecture 8. Yeah, in which to find the potential difference, we need to use the equations of V. Yeah, should be equals to negative integrations of E dot dl. Yeah, if you can recall back the equations where we have 2 points. Yeah, 2 points. We have the point of A and the point of B. Okay, this is where we need to find the potential difference between 2 points, yeah, where we have two distinct or two finite point of A and B. So the same things applied here in this example. Yeah, we need to use this equation to find the potential difference. But the point of A and the point of B need to be modified according to these questions, in which we are requested to find the potential difference between point of P and the point of origin, in which origin is taken as the reference, yeah, reference. So for that, we need to modify this equation, in which these equations will become as V as negative integrations of E dot dl, and the reference should be a starting point where it should be the origin. So I put O here as the origin, right? As the origin is O, and the end point should be the P. So that should be the potential difference between 2 points of P and O. Okay, so I just put here as a subscript to the V should be a PO, yeah. So PO, which is a potential difference between the point of P and the point of O, which is the origin. Okay. So for this, we know that there should be two sources of potential, yeah, two sources of potential, which are the positive rho L, and secondly is a negative rho L, yeah. So I have to segregate the calculation of potential difference according to these two sources of electric field or potential. Number one is due to the positive charge rho L, and secondly due to a negative charge of rho L. So we need to obtain what should be the potential difference due to the first source of positive rho L, and secondly the potential difference due to this negative rho L charge. Okay, so for the first source, which is a positive rho L, we're going to have the Vp naught, yeah, or Vp0 or Vpo should be negative integration of O to P, and the E, because the line charge is infinite in length, yeah, given to be too long, yeah, two long parallel wires. So we can assume that this line charge is infinite in length, and as what we have learned previously in chapter 2 and chapter 3, that the line charge contribution to E field will be rho L over 2 pi epsilon naught of R direction of R, yeah? So that should be the E field intensity reading for a line charge of infinite length. So we just use this E field in these equations here, yeah? So we're going to have rho L over 2 pi epsilon naught of R direction of R, and the dl, because your E is in the R direction, so your dl should also be in the R direction, which will give us the R direction of R. And if we proceed with the integration, we're going to have rho L over 2 pi epsilon naught. Okay, so now we have to be very careful on the selection of this integration. So the point of O, which is this origin, is having a distance of S from this rho L charge. So this point of O shall be now substituted as the S, which is a distance, a distance from the charge of rho L to the point, which is the origin. So that should be S. Okay. And then for the point of P, yeah, for the point of P here, you need to find what should be the distance, yeah, which is the radial distance from the point of P to the charge. So based on this diagram, you know that the distance is R1. Okay, so we have substituted the position of O and P with its respective distance. In this case, it should be a radial distance because we are following the definition of this R. Yeah, from what we have learned previously in chapter 2 and 3, R must be a radial distance from the line charge. Yeah, so for that, we're going to have S and R1 for both, for respective distance from the origin and the point P. Yeah, so we're going to have this, and we're going to have the solution for the Vp naught due to a positive rho L to be rho L over 2 pi epsilon naught, yeah, ln of R1 over S. Sorry, we have a negative sign there. Sorry for that. Negative sign. So I need to change the orientation of these, the ratio for that, in which we're going to have S over R1, yeah? Yeah, S over R1. Okay, along the way, if you have any question, just ask, yeah? Okay, of S over R1 in units of volt, the potential difference between 2 point P and O, which is due to the positive rho L. Okay, we shall then proceed with the next charge, which is a negative rho L. So contribution of potential difference Vp naught due to negative rho L shall be written as Vp naught of negative integrations. Again, you're going to use integration from 0 to P, and the rho L shall be written to be a negative rho L now, yeah, because we are having a negative rho L charge, over 2 pi epsilon naught of R, direction of R, and dl to be the R direction of R. Yeah, so for this, we're going to have a rho L over 2 pi epsilon naught, okay, and the integrations of 1 over R dr. Okay, so we need to obtain what should be the distance of the point of O and the point of P from the negative rho L charge. So evidently from this diagram, it shows that a distance of the origin from the negative rho L is S, yeah, whereas a distance of point P from a negative rho L charge is R2. So then we shall substitute the O with the S, and the point of P here should be substituted by the distance of R2. Okay, so if we proceed with this, we're going to have rho L over 2 pi epsilon naught ln of R2 divided by S in volts unit. Okay, so that should be the potential difference contributed by positive rho L given by this flow, and the next is a potential difference given by a negative rho L, which is given by this flow. So we need to add them up together because we're going to find the total potential difference. So for this, you can see that the VPO, the total potential difference, will be a summation of these terms and also these terms down here. So we're going to have rho L over 2 pi epsilon naught, okay, ln of S over R1, plus rho L over 2 pi epsilon naught ln of R2 over S. So evidently from here we can say it's a similar pattern, similar terms of rho L over 2 pi naught ln of S. So end up we are going to have the solution for this, yeah, will be written as rho L over 2 pi epsilon naught ln of R2, okay, R2 divided by R1. Okay, so that should be the case in which ln S terms has been cancelled out due to this summation. Yeah, so that should be the answer for potential difference between the point P, yeah, and the origin in the terms of R1 and R2 as requested from the questions here. Okay, any question for these solutions of potential difference? So the idea of solving the potential difference problem is using these equations that we have seen earlier in lecture 8 videos, yeah? Okay, so if there's no questions, I shall proceed with the next example. Okay, so again, we are dealing with the problems related to potential. So you need to ensure that you have a good understanding on the potential topics before you can proceed with lecture 9 after this. Okay, in this example, this is taken from the previous test questions. We are given a simple coaxial cable, yeah, coaxial cable, which is made up of a conductors, a cylindrical form of 5 millimeters diameter, yeah, 5 millimeters diameter, with an outer conducting sheet, also cylindrical, coaxial with the central conductors. So basically, we are having two conductors, yeah, two cable which are coaxial. Coaxial means that they are having same axis, yeah. So the internal diameter of the outer sheet is 20 millimeter. The space between the two cylinders is filled with air, and the maximum voltage that can be applied between the two conductors is 500 volt. Okay, so let us sketch this problem first. So we are having the first conductor inside the first conductor, the first coaxial cable. The first cable is having a diameter of 5 millimeter, or we can have a radius. Yeah, we can have a radius of 2.5 milli. Yeah, I put milli here. Right, and then we are having another conductor which is having the internal diameter of 20 millimeter. Okay, so we can have another conductor here. Sorry, not that nice, my drawing of this cable. Okay, that should be another cable here. Okay, so that should be two cable. The first one is here. That should be the cable number 1. Yeah, cable number 1. And here is your cable 2. Yeah, that's what we call here this particular cable as coaxial cable. Yeah, two cables having same axis. Okay, so before that, let us proceed with the labeling for the diameter or radius for the outer sheet. Given that the internal diameter, yeah, internal diameter of the outer sheet. So this is the outer sheet, yeah. Number 2 is the outer sheet. Given that the internal diameter is 20 mm, which means that the internal radius is equals to 10 millimeter. Okay, so that should be the sketching, yeah, for these particular problems. Okay, so we proceed. I rephrase the sketching, which is a 2.5 milli, the radius for the internal conductor, and 10 milli is the radius for the internal radius for the outer conductor. Okay, hopefully you understand, yeah, from the given question. Yeah, so you must be able to sketch the given problems clearly. Okay, given that the maximum voltage that can be applied between the conductors is 500 volt, which means that in between the conductors, yeah, given that the conductors is filled with air, yeah, given that, if I can recall, yeah, the space between the two cylinders is filled with air, which means that inside this region between 2.5 milli and 10 milli radius, the region is filled with air, and it's given that the maximum voltage that can be applied between the conductors is 500 volt, which means that the maximum voltage, the Vmax, that can be applied, which equals to 500 volt. Okay, so that should be the information given in these questions. Yeah. Okay. So based on these given questions, A is to find the electric field strength at the surface of the inner conductor. So the inner conductor is having a radius of 2.5 milli. Yeah. So electric field strength means electric field intensity E. Yeah. So that is E field intensity. That's what meant by these questions. Yeah. Okay. All right. So how to find the E field strength at the surface of the inner conductor? So which means that we need to find what should be the E field at E field at R equals to 2.5 millimeter. Okay, so that is what meant by this question A. What should be the E field strength at the surface of the inner conductor, which is the E field at the radius of 2.5 millimeter. So that should be the questions. Okay, so in this particular case, we are not given any information about the charge distributions, right? Yeah, what is the charge distributions in this particular problems? We are just given the maximum voltage which can be applied within these two conductors. So this is the only information given from the question. So how can we find the E field from the given information of Vmax here? Okay, so what we can do now is that we can assume that because we are dealing with the conductors, and we're going to learn in chapter 5 later on that on the conductors, the charge will only exist on the surface of the conductors. The charge will only exist on the surface of the conductor. So this is a special characteristics of conductors which will be learned in chapter 5 later on, within 2 or 3 weeks time from now. Okay, so for that, knowing that this inner structure is a conductor, so we can assume that this particular conductors is having a charge of rho s on the surface of it. Yeah, so we can label that here on this particular surface, there's a charge of positive rho s. Okay, so that is our assumption. Yeah, so which means that that should be the charge rho s. Yeah, on this conductor surface. Right, so for this particular case, we can use information of this rho s to find the E field within the region of 2.5 and 10. Yeah, between 2.5 and 10. Okay, because we're not given any information about the length of this coaxial cable. So by right, we can assume that the length is infinite, yeah, or is too long. So we can use the Gauss law to find the E field between 2.5 milli and 10 milli radius. So our task now is to find the E field, yeah, for the region between 2.5 millimeter and 10 millimeter, which is the region between the two conductors. Yeah, right. So from here, by using the Gauss law, we can sketch the Gaussian surface. Okay, so that should be our Gaussian surface. Yeah, to which is having a radius of r. Okay, radius of r. Okay, in which we're going to have the d dot ds integration will give us enclosed charge. Okay, and by using Gauss law for a cylindrical system of coordinate, we can further write that the left-hand side can be written as dr of 2 pi rl, okay, in which we assume that the length for the Gaussian surface is L. Okay, so I don't have to write the full version for the left-hand side integration, yeah, because we have done this a lot in lecture 6 before. So if you have a problem with this, please refer to lecture 6 and the videos on this. Okay, and for the enclosed charge, which is a charge enclosed by the Gaussian surface, you remember that this is the integration on the Gaussian surface. Enclosed charge is a charge inside the Gaussian. Okay, and we are saying that the enclosed charge should be equals to rho s, okay, which is your surface charge density. Okay, and then the ds, which is the surface area for your curve surface, should be equals to 2 pi, and r will be 0.005, yeah, because of 5 milli, yeah, and L should be there. Sorry, not 2.2, not, sorry, my mistake. Not 5, but it should be 2.5, yeah, because this is a radius. Okay, this should be 0.0025 L. Okay, that should be the correct one, yeah. Okay, so 2 pi can be cancelled out, L can be cancelled out. So we are having that the dr shall be written as rho s of 0.0025 divided by the r. Okay, and from here we can write that the vector d shall be equals to dr direction of r, which will give us rho s times 0.0025 divided by r direction of r. Yeah, and subsequently you're going to have the E field shall be equals to d over epsilon naught based on relationship between the d and E, and this will give us rho s 0.0025 over epsilon naught r direction of r volt per meter. Okay, so that should be your E field terms, the E field equation for a region between 2.5 milli and 10 milli. But this yet to answer our question, because the question is to find the E field at 2.5 millimeter. So we still cannot find the E field because you have unknown of rho s. Yeah, rho s is the unknown. So by right, you need to find the rho s in order for us to find the E field at 2.5 millimeter. So how to find the rho s terms or rho s value? So that is what this is the importance, yeah, the importance of the given Vmax in these questions. Okay, so we know that voltage that can be applied between the conductors basically should be a potential difference, yeah, potential difference between the two conductors. Okay, that is what meant by the maximum voltage that can be applied between the two conductors. So in this particular case, we can see that this particular information, Vmax, by right, can be written as negative integrations of E dot dl, which is a potential difference between the surface of 2.5 milliradius and the surface of 10 milliradius, because that's what meant by this sentence here. Maximum voltage that can be applied between the two conductors. So the two conductors is between 2.5 milli and 10 milli. So the Vmax is measured between 2.5 milli and 10 milli. So for that, we can see that the integration of the E dot dl, yeah, for the 500 volt maximum voltage should be integration between 10 milli, okay, 10 milli and 2.5 milli. Okay, that should be the range of your potential difference, yeah. Right, so from here we can use the E field, yeah, because this is the E field that we have obtained previously, and this E field is the E field equation within 2.5 and 10 milli. So by right, we shall use these E field terms. So we can write that the Vmax shall be equals to 500 given from the questions. And then we're going to have a negative. The E will be, so 10 milli, this is 2.5 milli. The E field shall be using this equation of E field, which is rho s 0.0025 divided by epsilon naught of r, direction of r, and the dl should be dr direction of r. Okay, so I believe that from here we can use this equation to find the rho s, right? So we are having now that the 500, I'm using this side now, yeah? For 500 shall be rho s, okay, multiply over epsilon naught, sorry, 0.0025, and we have a ln of r, okay, and since we have cancelled the negative sign, so it should be 2.5 milli to 10 milli. Okay, right. So from here, we can proceed with the calculating the rho s, in which the rho s can be written to be equals to 500 multiplied with epsilon naught divided by 0.0025, and we have to multiply or divide still with a ln of 4, yeah? Ln of 4 because 10 over 2.5 is 4. So that should be your rho s in coulombs per meter squared unit, surface charge density, yeah? So that's how you obtain the rho s. So this rho s, please help me calculating this rho s for me, okay? And subsequently we can find the rho s, yeah? And this rho s shall be now substituted here, yeah, on these equations of E field, okay? So by right, I need to use what should be the proper space to be used here then. Okay, so I'm using this space here. So at r equals to 2.5 millimeter, yeah, millimeter, sorry, your E field shall be equals to, yeah, based on this equation here. So rho s is what we obtain here. So let's say we put rho s naught, yeah, rho s naught. So please calculate the rho s naught for me. So rho s naught should be there. Okay, multiply with 0.0025 divided by epsilon naught of r. So r shall be equals to 0.0025 in the direction of r, yeah? Okay, because r is at 2.5 milli. So just substitute r of 0.0025. So we can cancel this out. So we're going to have the E field at 2.5 milli will be rho s naught over epsilon naught in the direction of r volt per meter. So rho s naught is based on what we have calculated down here. Okay, is that clear on the solution for part A? So it's quite long, yeah? But that's how we solve the questions based on the given information of the maximum voltage applied between the conductors. Okay. Any questions so far?
Doctor.
Yes.
For the limit of integration, y is from 10 milli until 2.5 milli. It's not the 2.5 milli until 10 milli.
Okay, so you have to go back to definition, yeah? Definition of the equation here, where V is negative E dot dl. Okay, it's understood that based on this equation, that V shall be flowing, or the value of V should be inversely proportional with the E field, which means that, for example, yeah, if we have a point charge, don't have a proper, okay, I'm using this slide here. If you have a point charge here, right, we have the E field, okay, point charge of Q, for example, sorry, charge Q. So the E field is in this direction, yeah. So to find the potential, let's say you want to find a V of negative E dot dl. Okay, negative sign here means that the potential shall be calculated inversely. I mean, we need to find a ratio of electric field from a smaller value to a higher value. Let's say we have 2 points here, let's say point A and point B, right? So to find the potential between these 2 points here, your integration must be starting from the lower value, B, to the higher value of A. That's why we have a negative sign here. Okay, so that's the reason why. Yeah, so back to this question just now, why we need to integrate from 10 to 2.5, not the other way around, is because of this argument. Yeah, in which if you want to find potential difference between 2 points, we need to understand, we need to know what is the direction of the E field. I mean, what is the maximum value of the E field? So if the maximum value of the E field, let's say, is point of A, So your integration must be from the lower value, which is from B, and the endpoint should be at A. Okay, and that's why if we base on this, we know that the E field is in the R direction, right? In the R direction, which means that further away from the center, yeah, in which the R is increased, yeah, the R is said to be increased, so the E field will be reduced, yeah. So as the E field is reduced, that's why we are taking potential difference. The integration will be from the smaller electric field intensity to higher electric field intensity. Okay then,
Okay,
Rehan?
thank you.
Okay,
Okay, thank you.
okay, you're welcome. Okay, so hopefully you understand this concept, yeah? So this, you need to understand this concept very clearly. Thank you, Rehan, for raising this queries. Very good question, basically. Okay. For part B of the question, which is to find the electric field strength at the inner surface of the outer conductor. Okay, so I think we need to use the same method, but you don't have to proceed with all of these calculation because you have obtained the rho S naught earlier, right? Yeah, so rho S naught has been obtained. So this rho S naught can still be applied for the part B of the question. Yeah, so the inner surface of the conductor is at the radius of 10 millimeter. Yeah, at 10 millimeter. So for that, okay, I need to erase this portion. Sorry. Okay, need to erase this portion here. Okay. Okay. So for at R, yeah, at R equals to 10 milli, okay, 10 millimeter, which is at the inner surface of the outer conductor, we can say that the E field will be equals to rho S naught. I'm using this equation still, yeah, this equation, okay, in which rho S is rho S naught. So we're going to have rho S naught divided by epsilon naught, and then we have a 0.0025 divided by R. So now R shall be 10 milli, which is 0.01, yeah. Yeah, okay, and then this is in the other direction, so we can have the E field shall be rho S naught over epsilon naught, so that will give us 0.25 in the other direction. So that should be your E field in volt per meter, in which the rho S naught is similar to the rho S naught that we have obtained earlier. Okay, so by multiplying the rho S naught with the 0.25 and divided by epsilon naught, so you're going to get the E field at a 10 millimeter surface. Okay, is that clear on this solution? Okay, it's similar to the previous part here. Yeah? Just we just change the position, the point of interest. Okay, so we go for the part C of these questions. Yeah. All right. So erase all in this slide. Okay, we proceed with this part C. Now it is said that the maximum applied voltage has been increased to 1000 volt. Yeah, so we have increased the applied voltage to 1000 volt. Previously it's 500. Now we change it to 1000 volt. We increase it to 1000 volt. The question is determine the new internal diameter of the outer conductor so that no electrical breakdown will occur. Given the maximum permissible electric field at any point between the conductors is 3 times 10 power of 5 volt per meter. Okay, so now based on this information, we can extract the important information is, one of them is the Vmax is equals to 1000 volt now. Okay. And then we are given that the maximum permissible electric field, where we have the E field maximum at any point between the conductors. Yeah, Emax between 0.25 milli and 10 milli. Yeah, the Emax within this region is given by 3 times 10 power of 5 volt per meter. Yeah, because between the conductors means a region between 0.25 milli and 10 milli. Yeah, so this is the region between the two conductors, which is filled with air. Okay, so that should be the maximum E field. Okay, so these are two informations given from the question. So now Determine the new internal diameter of the outer conductor. New internal diameter of the outer conductor. Okay, so it means that previously the internal diameter of the outer conductor is 20, right? Previously the internal diameter, okay, I put it here. Previously the internal diameter, okay, internal diameter, okay, sorry. Okay, so D internal, yeah, internal. So D is known to be diameter, lah. It's about given to be 20 millimeter. Okay, 20 millimeter. So you need to find what should be the new D internal, yeah, so that when we are having a maximum applied voltage of 1000 volt, there should be no electrical breakdown occurred in this particular coaxial cable. Okay, so this is basically a question related to a design, yeah, related to a design. So it's a very good question, basically. Okay, we know that previously from the part A and B just now, we have calculated that the terms for the E field, the equation for the E field, is given by rho s naught. Sorry, not rho s naught, it's a rho s, yeah, rho s. Okay, it's a rho s. Then we have 0.0025. Okay, bear in mind that there should be no changes on the internal, on the radius of the internal conductor. Yeah, the radius or the diameter still the same, which is 5 millimeter. Yeah, so no changes for this diameter of the internal conductors. And then we have epsilon naught of R. Yeah, direction of R. So that should be the E field given. Yeah, E field that has been calculated, the equation of the E field. Okay. So given that the Emax is 3 times 10 power of 5 within 0.25, and I shall put a new lah, yeah, not 10 now, it's a new, let's say R naught lah, yeah, let's say R naught. R naught is a new radius, yeah, a new radius, yeah. Okay, so based on this, we can say that the maximum E field, yeah, the max E field can happen at the smallest R, right? Okay, maximum E shall be at smallest R. Based on this equation here, we're going to have the maximum E field when we have the smallest R. So for that particular case, knowing that the smallest R that it can be is at 0.25, right? So for this, we can say that the maximum E field, which is 3 times 10 power of 5 volt per meter, will happen when the R is at the max, is at the minimum, which is at 0.0025 radius, which is at 0.0025 radius. Okay, that's how we obtain the maximum E field, where in which we put that the R should be the minimum, sorry, should be at the minimum, which is at 0.025. Yeah, so this can be cancelled out. So we're going to have that the rho s will give us 3 times 10 power of 5 of epsilon naught. Not sure what's the problem with my tab here. Okay, sorry for that, yeah. So we're going to have epsilon naught terms there in coulombs per meter squared. Okay, all right. So hopefully you understand, yeah, why we can have this value of rho s, yeah, because we are using this understanding that the Emax will happen at the minimum R, which is at 0.0025. Okay, so this rho s will be very important because we're going to use it to find the potential difference. Yeah, so we know that from the equations of V of negative integrations of E dot dl. Okay, E dot dl, right? E dot dl. So we're going to have the V max is 1000 volt, and that will be negative integration. So the starting point is unknown because we're not sure what should be the new value. So we put just as R naught as we have used just now, R naught, yeah, just put as R naught. And the endpoint will be at 0.25 milli. Okay, sorry, 0.0025, or I just put it as 2.5 milli. Yeah, 2.5 milli. So hopefully you understand, yeah, 2.5 milli here. Okay, and the E field will be, we just use the rho s here. So rho s of 3.5, 3 times 10 power of 5. Okay, so 3 times 10 power of 5 epsilon naught, that should be our rho s. And we have 0.0025 divided by epsilon naught of r, dr, and the dl will be dr direction of r. So that should be the E field used. Yeah, I'm using the E field here. Yeah, that's how you have these terms here. Yeah. So this can be cancelled out, the epsilon naught. Okay, so end up you're going to have 3 times 10 power of 5 multiply with a 0.0025. Okay, and the ln of r, which will be having a ratio from r naught to 0.25 milli, yeah, because we have cancelled the negative sign. So by cancelling negative sign, we just change the integration from 0.25 to r naught, yeah, right? Okay, so from here we can proceed with the calculation. So we're going to have the value for this v of 1000 just now. Okay, so I put it right. We have 1000, yeah, 1000 equals to so 3.5. So 3 times 10 power 5. That should be, yeah, 7.5 times 10 power of 2. Okay, right, and then we have a ln of r naught divided by 0.25 milli. Okay, so end up we're going to have ln of r naught, okay, uh, shall be equals to 1000 divided by 7.5 times 10 power of 2 plus ln of 0.25. Sorry, my mistake still here. It's not 0.25 milli, it's supposed 2.5 milli, yeah? So that should be 2.5 milli, and that should be also 2.5 milli. Okay, and then we have a ln, this is 2.5 milli, yeah? 2.5 milli. Okay, right, so that should be how you obtain the ln of R naught, and subsequently you can find the R naught, okay, in which we are supposed to get, I'm using this side here, in which the R naught shall be equals to exponential of 10 over 7.5, okay, and then plus ln of 2.5 milli. Okay, so that's how you obtain the R naught unit, I mean the R naught value. So basically the R naught value from this equation, it should be in meter. Okay, so you can have the answer in meter or in millimeter, depending on your answers. Yeah. Okay, so that's how you obtain the R naught, which is the new radius. Yeah, the new radius for the inner diameter. So the inner radius for the outer conductor, or you can multiply with 2 to find the internal diameter. Okay, so that should be the radius or the diameter for the outer conductor. Is that clear on this solution for part C? Any questions so far?
Doctor,
Yes.
for the outer shell should be ground or what? The potential of the outer shell outer shell should be 0 or ground. I'm confused.
The outer shell, do you mean the outer conductor?
Yes, the outer conductor.
Okay, so
E,
basically, yeah.
yeah.
Yeah, Yang Yu, okay, proceed please, your question. Oh, okay. So we are supposed to get, if I can, okay, I need to erase this Okay, basically the questions, if you can recall back, should be given by this diagram. The internal conductor, which is a 2.5 milli radius. Then we have another conductor, okay, another conductor, all right, and for this internal radius will be 10 milli. Okay, our concern is only within, okay, as mentioned just now, that should be our first conductor and that should be our second conductor, right? Okay, our concern in these particular questions is given that is based on the potential given in this region, the Vmax, which is given between a 2.5 millimeter radius and 10 millimeter radius of the conductor. So our concern is not on these conductors. So you don't have to worry on that. Whether it's a zero potential or anything. Because our concern is to find the potential difference between these 2 points, let's say at this 2.5 milli and 10 milli. That's why if you can recall back to our solution just now, we have negative integration from 10 milli to 2.5 milli of E dot dr. Okay, so we just concentrate on this region between 2.5 milli and 10 milli. So you don't have to consider this region which is bigger than 10 millimeter radius. Is it okay, Jiang Yu?
Okay, doctor, understand.
Okay,
So
thank you.
in the real case,
Yeah.
so normally the outer conductor will be connected to the ground or
Correct. It should be connected to the ground. Correct. You are correct. Yeah. Because in a charge, I mean a system of charge with equilibrium, basically, if we have a positive rho s charge in here, you are supposed to have negative rho s charge on the outer surface. So due to this particular case, there should be no charge elsewhere. Yeah. So we have positive rho s and negative rho s. So when using the Gauss law, basically there should be no electric field outside. The field will be zero. Okay, yeah, by using the Gauss law, yeah, it's understood that we have a positive rho s, a negative rho s. So due to that, when we calculate, when we use the Gauss law to calculate the E field outside these conductors, yeah, outside these conductors, okay, so the value of the E field will be zero. And basically, this particular cable outside will be grounded. Just correct.
understand, doctor, understand. Thank you.
Okay, okay, welcome. Okay, any more questions on this example? So this is very good example. And this kind of question has been tested before in the test assessment. Okay, I'm not sure what kind of question will be tested next week. So yeah, so don't worry on that. Hopefully, if you understand the concept very well, yeah, you should face no problem. Supposedly, in solving the given questions. Yeah. Okay, so I think we have done with the potential and also potential difference. Okay, and we can now proceed with lecture 9. So lecture 9 basically will be covering these two topics, which is on potential gradient and energy density. But for this week, yeah, I will just proceed with the potential gradient. Okay, and energy density will be covered on Tuesday. Yeah, on Tuesday. Okay, so these will be the topics that we have that I've mentioned to you before in lecture 8. Okay, so if you can recall back, we have learned about the concept of potential difference and potential, and then we are now going to cover these topics. Basically, energy storage in the field, and the idea of energy exchange, gradient, and energy within the system of charges. Yeah. So our concern for lecture 9 today will be only on the gradient. Yeah, the gradient. Yeah, energy within a system of charges or energy storage in the field will be covered next week on Tuesday. Okay, so that should be lecture 9. Potential gradient will be the topics to be learned today. All right, so motivation for this lecture 9, basically I restrict it only to enable the students to calculate the electric field using the potential value. Okay, so that should be the only things to be learned today. Yeah. Enable the students to calculate the electric field using potential value. Okay, so just to inform you that this lecture 9 will not be tested, will not be assessed in your test 1. Yeah, so the assessment for test 1 will be covered until lecture 8 only. Okay, right. So next week on Tuesday we're going to proceed with the concept of energy density in electrostatic field. Yeah. Okay, so objective for today will be only related to the first objective, in which we want the student to understand or able to calculate the electric field intensity using the potential value. Okay, right. Okay, you must be able to calculate the E field intensity using the potential value. So that is the important things from these topics of potential gradient. Okay, so we just recall topics that we have learned previously in chapter 2 and chapter 3, in which if we have a charge distribution, we have a point charge, we have a line charge, we have a surface charge, and we also have a volume charge. Yeah. So we can use this charge distribution to find the E field intensity by two methods or two laws. Okay. The first law is the Coulomb's law, okay, that we have learned in chapter 2. And then we also have the Gauss Law, which we have learned recently in chapter 3. And I hope that all of you have understand this Coulomb's law and Gauss law clearly. Okay, and previously in lecture 8, we have learned that by using the charge distribution, we can use it to find the potential. Okay, we can use this equation, V equals to dq over 4 pi epsilon of r, in which the dq can be in terms of rho L dl, it can be rho S ds, or it can be rho V dv, or it can be just a point charge. Yeah, initially we have learned that this equation comes from equation of V of q over 4 pi epsilon of r. So this is the fundamental equations. Yeah. And also, if you can recall back, the potential can be based on this equation, a negative E dot dl also, where we have the initial point is at infinite, and we can find the potential at a point of A. So this is potential at the point of A, in which the reference point is at infinite. Yeah, so this is the equation. So basically, this equation and these equations that we have seen here are the same equation. So these are two equations that can be used to calculate the potential. Yeah, in which basically by using the charge distribution information, we can use it to calculate the potential. This is what we have learned in chapter 4, lecture 8, sorry, lecture 8. Okay, so for these topics of gradient, basically we want to use the potential V, yeah, that we have. Yeah, let's say we have potential V. We can use the potential V to find the E field. So this is what we're going to learn in this first part of lecture 9. Yeah, use the V to find the E field intensity. Yeah, right. So this is what we're going to learn in this first part of lecture 9. Okay, so just to recall back the things that we have learned previously. Yeah, in which if we have the point of A, yeah, the point of A, we have a charge of Q, which say that the charge and potential at point of A is given by Q over 4 pi epsilon of R, in which, if we can recall back, it is based on this equation where the V of point of A is given by negative integrations of E dot dl, yeah, integration from infinite to the point of A, which is given by negative integration infinite to the point of A of Q over 4 pi epsilon naught of R, power of 2 direction of R, and dl will be dr of R. So we're going to have Q over 4 pi epsilon of R, which is from infinite to the point of R, because the distance, yeah, from charge Q to the point of A is R. So we're going to have infinite to the point of R, and for solving this will lead to these equations. Yeah, that's how you obtain the potential of V, a potential at the point of A given by Q over 4 pi epsilon of R. So the basic equation that leads to this formation, as I mentioned before, is this, where we have V as negative integrations E dot dl. Okay, so if we consider that we are using the Cartesian systems, yeah. So for Cartesian system, for instance, we have the E field will be recalled, will be written as Ex direction of X plus Ey direction of Y plus Ez, sorry. Okay, plus Ez direction of Z, yeah. right? That should be the E for Cartesian system, and also for the DL, we can have it as a dx direction of x plus dy direction of y plus dz direction of z. So when we have a dot product between these two E and DL vectors, we are supposed to get the V will be written as negative. Okay, that should be written as integration. Yeah, integration of ex dx, okay, plus ey dy plus ez dz. Okay, in other terms, if we base on this, we can say that basically the V will consist of x component, y component, and a z component. Okay, in other words, I can say that the Vx, yeah, will be equals to, sorry, the dVx, sorry, yeah, will be equals to the ex dx, okay, and then because we have integration, right, so the integration can be vanished by simply put a dVx here, negative, sorry, I put negatives there for the negative ex dx. Also going to have a dvy will be negative ey of dy, and also the dvz will be equals to negative ez of dz. Okay. Okay. So from here, we can say that the ex, yeah, the ex, yeah, from this equation here, the ex will be equals to negative dvx over dx. Okay, and so we're going to have the ey will be negative dvy over the dy, and also ez will be also equals to negative dvz over the dz. Okay, so that's how we obtain relationship between the E and the V. Yeah. Okay, so basically from here we can introduce one operator which is called as a grad operator. Yeah, grad operator or del operator, in which this del operator will be written as d over dx of x is a vector. Yeah, it's a vector plus d over dy of y. Okay, plus d over dz of z. Okay, and if we combine these terms and this del operation, we can say that the E vector basically can be written as a negative dEx over dx of x, sorry, dvx over x of x minus dvy over dy of y minus dvz over dz of z. Okay, so we can see that this operator here, yeah, we have a del operator, right? And if we can combine these two operations here, we can write that the E field basically can be written as equal to negative del multiplied with the V. So this operation where the del multiplied with B is called as gradient. Okay, or in other words, in a simpler word, the E field can be calculated by simply evaluating the negative of gradient of the V, or gradient of the potential. Okay, so this is the equations of potential gradients in which we can find the electric field intensity E by simply evaluating the negative of grad, yeah, negative of the gradient of potential V. Okay, so what I've shown here is the mathematics behind the formations of this equation, yeah, that lead us to the equations that enable us to find the E field, in which we are using the potential V equation. So if you go back to this slide just now, yeah, you can see that to find the potential, to find the E field now, so we have three methods. We have the Coulomb's law in chapter 2, we have Gauss law in chapter 3, and presently we have the third method to find the E field, which is the potential gradient, in which the E field will be based on negative grad of V. So if we know the potential value, we can use the potential value to find the E field. Okay, so that's the importance of the gradient method, gradient technique to find the E field. Okay, okay. So let us proceed with this slide. Okay, so this is the equation just now. So that is what I mentioned, yeah, previously, the mathematics behind it. This is the equations mathematically, a negative of grad of VA, and the grad basically will be depending on the coordinate systems. Okay, so we have the gradient operation for the for Cartesian. This is the equation. Gradient for cylindrical and gradient for spherical. Okay, you don't have to memorize this gradient operator for each coordinate systems. You will be given if requested. Yeah, yeah. So you don't have to memorize this. Yeah. So the conclusion from this slide is that the third method used to calculate the electric field will be the potential gradient, in which we need to know what is the potential value at a point, which we can use the potential equation, the gradient equation, to find the electric field at that position. Yeah. Okay, so let's have a look at this example number 1 to ensure that you really understand on this concept of potential gradient. Okay, let's have a look at this example. We are given that the V, which is a potential, is x squared y multiplied with z plus 3. Okay, so we need to find the E field intensity at the point of 3, 4, and -6. Okay, so since we are given the V, we can use it to find the E field, yeah, by using the gradient, in which the E field will be simply equals to negative grad of V. Yeah, and we know that this problems is related to Cartesian system, yeah, because your V is in Cartesian and also your point, the point of interest is also in Cartesian, so you need to use the gradient in Cartesian. So that should give us negative dv over dx plus, dvx over x, dv over dx direction of x, plus dv over dy direction of y, plus dv over dz direction of z. Okay, so we have to differentiate the dv with respect to x, y, and z. So that will give us negative. Okay, for dv over dx will give us 2x y of z plus 3 direction of x, plus dv over dy, we differentiate this v, we are going to have x squared z plus 3 direction of y, plus differentiation of v respect to z for these terms, we are going to have x squared y only, yeah, in the direction of z. Okay, so remember that the E field should be in a vector form, yeah? You need to put x, y, z. If you base on this gradient, here we also have x, y, z, yeah? For this Cartesian system. Okay, so that should be your E field terms. So simply at point of 3, 4, -6, we just substitute that at x equals to 3, y equals to 4, and z equals to -6, you can find the E field by simply substituting all of these value into this equation, yeah? So substituting x equals to 3, y equals to 4, z equals to -6, this equation will give us the E field at the requested location. So that should be the E field in volt per meter. So please help me substituting the value and you're going to get the E field, yeah? Okay, so part B of the question, this is part A just now. So part B is to find a charge within the cube, in which the cube is given by x from 0 to 1, y is also from 0 to 1, and z is also from 0 to 1, yeah? So if you can sketch your cube, somehow it should be sketched to be look like this is y, this is x, this is z. So your cube should be look like this, yeah? Okay, so 0 to 1, 1, and 1. So that's how the cube should look like. Okay, so how to find the charge within the cube? So for this, you have to go back to the basic of Gauss Law, or I can say the modification of Gauss Law, which lead us to the divergence equation, yeah, the first law of Maxwell. Ihsan Aulia Rahman, are you in my class now?
Yes, doctor.
Okay, please help me. Can you please rephrase for me the first law of Maxwell?
Sorry, doctor, I don't quite remember.
It is in lecture number 7. So have you do a revision for lecture 7?
No, doctor, I haven't.
So very sad to hear that. Yeah. So please, Isan, you have to work hard. Yeah. Okay.
Yes.
Can I ask Jinghui, New Jinghui? Are you in my
Yes,
class?
doctor.
Okay.
Yes.
Please help me. Can you please rephrase for me the first law of Maxwell?
The equation. The
Yeah, the equation. Correct. The
the
equation for
the the grade dot
the
grade
divergence. Yeah.
then the inverse triangle that I dot
Mm-hmm.
D equal to rho V.
Thank you very much. So this is the divergence equation, or also known as first law of Maxwell. So if you can recall back from lecture 7, I did formulate this equation starting from the Gauss law, yeah, the d dot ds equals to enclosed charge. Yeah, so I formulate this equation based on this Gauss law. Basically, this equation and this equation of Gauss law are the same. Thank you, Jinghui, for your answer. Thank you very much. Okay, so that should be the equation of first law of Maxwell, right? So you're going to use this equation to find the charge within the cube of x, y, z from 0 to 1. Right. So the purpose of using this equation is that by using the divergence of D, we can find the rho v, the charge density in coulombs per meter cube. And from this rho v information, we can use it to find the charge, in which the charge Q can be calculated by simply using the integrations of rho v dv. So that's the idea. Yeah, that's the idea. So we need to find the divergence of D first, and afterwards we can use the rho v obtained and use the integration of rho v dv to find the charge. So that's how we solve for the charge within the cube of x, y, z from 0 to 1. Okay, so let us proceed with this divergence operation for the D. So we know that the D will be equals to epsilon naught of E. Yeah, we have the E field from the first part just now, from the part A just now. So from the D, from this E field, we can use it to find the D. And afterwards, we can find that divergence of D shall be written as D of dx divided by x, d dx over dx plus d dy over dz plus, okay, plus d dz over dz. Okay, so that should be the divergence of D. Yeah, remember, divergence will give us a scalar. It's not a vector. Yeah, will give us a scalar. Okay, so now we proceed with this differentiation of dx with respect to each dx, dy. So this is dy, yeah? dy, sorry, dy and dz. So for the dx, you have these terms here. So when you differentiate with respect to x, you're going to have a negative 2y z plus 3. And for this particular case, for dy over dy, okay, so that is, sorry. So that should be my dx, that should be my dy, that should be my dz, yeah? Okay, so if we differentiate dy with respect to y, so that will give us 0, yeah? Because there is no dy, there's no y terms here. When you differentiate towards y, we're going to have 0. And similarly for the dz, when you differentiate towards z, this will also give us 0. So we only have this value for your divergence of D. So this is also equal to your rho v. Am I right? Yeah, that's your rho v, yeah, because we are based on this equation. So if we manage to evaluate the divergence of D and you get the answer, so that answer is equal to your rho v. So you're going to use this rho v to find the charge, in which the charge amount Q will be integrations of rho v dv, and this will be based on integrations of negative 2y z plus 3 of dx, dy, and dz. Okay, and if we proceed further, we're going to have a negative integrations of dx, integrations of 2y dy, integration of z plus 3 dz, in which all of these will be having a range from 0 to 1 with respect to the given cube size, yeah? 0 to 1 for x, y, and z integration. Okay, so please calculate this for me We're going to have the charge amount in Coulomb. Okay? So is that clear on this solution? So the idea from this is that we are giving you the V potential. Yeah, so for potential, you should be able to find the E field based on the gradient method. Okay, and from the E field, you use the first law of Maxwell to find the rho V, and from the rho V, you can use it to find the charge. Okay, so that is the basic ideas is this part A basically, yeah, which is based on these gradient operations to find your electric field intensity. Any question for this example? Okay, no
Doctor,
question.
can explain
Yes.
again why the dy over the delta dy over dy is equals to 0?
This one is it.
Yes.
Okay, you looking at this. Is there any y component for your dy?
Oh no.
Okay, so when you differentiate, you're going to have 0, right?
Oh yeah.
Yeah. Okay. Thank you.
Okay, thank you.
Right. All right. Is there any more questions? Okay, good. Thank you very much for the questions. Yeah. So hopefully that question will also have others. Yeah. Thank you very much. Yeah. Okay, we proceed to example 2 on this gradient method. Okay. So basically, this example 2 is related to example 1 in lecture 8. Given the potential at any point on the z-axis is V of rho L R naught of 2 epsilon naught R naught squared plus Z squared half. The question is obtain the E field terms at any point on the Z-axis and prove that the answer is similar to the given term in example 1. Okay, so if you can recall, but basically this is related to a case of let me see, example 1, yeah? I have to go back to example 1. Example 1 of lecture 8. Lecture 8, example 1. This is the one, yeah? Example 1. So we are giving you the ring uniform. Okay, this is the one, sorry. Ring of uniform rho L. Okay, so we go back to lecture 9. Okay, we are given the problems of a ring. Okay, problems of a ring. Right, having a radius of R naught, a charge of rho L, coulombs per meter, which is a ring, yeah? And that should be the axis of your ring. At this particular point, which is having a coordinate of 0, 0, z. So from the previous example 1, what we did is that we are calculating the potential. Yeah? We are calculating the potential here, the V at 0, 0, z. So you can recall, you can have a look at example lecture 8, the videos on how we calculate the potential V, in which potential V at this position is given by this. Yeah, yeah, rho L R naught. R naught is a radius, rho L is a charge density, a ring. Z is the position. Z is position on the x-axis. So basically, Z is a variable. Yeah, that is a variable. Any point on the z-axis. Okay. The question is obtain the electric field terms at any point on the z-axis and prove that the answer is similar to the given term in example 1. Okay. So basically, this is to find the E field if you are given the V. Yeah, which is to testify our understanding on the potential gradient method. So as what we have learned previously, to find the E field, if you are given the V, simply we just use equation of E equals to negative grad. I put grad, yeah, grad of V, grad of V, or also be known as gradient of V. Either one should be okay. Okay, so as what we have learned, the gradient of V will be depending on the systems of coordinate. So if you base on this, your coordinate system will be a cylindrical, yeah, cylindrical. So we have to go back to this slide, in which we have the equation for grad of V for cylindrical. So we have this, yeah, this is the grad of V for cylindrical, dV over dr of R, 1 over R dV over dV of V plus dV over dz of Z. Okay, so we can have that the E field will be written as negative dV over dr, direction of R, plus 1 over r dv over d phi, direction of phi, plus dv over dz, direction of z. Okay, that's how we calculate the E field. Okay, so based on this, we need to differentiate the V respect to R, respect to phi, and respect to Z. But looking at this given V, you know that the only variable that we have here is Z. Yeah. So this is your only variable that we have. Z. So which means that there is no R variable, there is no phi variable. So as such, we can say that the dv over dr can be 0, dv over d phi can also be 0, because the argument that there is no variable for the v, so differentiation of v with respect to r and phi, both of them will lead to 0. So we can then simplify our equation of E field to be equals to a negative dv over dz, direction of z. Okay, so we can differentiate this dv with respect to z. So we're going to have negative rho L R naught over 2 epsilon naught d over dz of R naught squared plus Z squared power of negative half. So we're going to have negative rho L R naught over 2 epsilon naught. So that will give us a negative half R naught squared plus Z squared and 2Z. Yeah. So 2 can be cancelled out. So you're going to have positive rho L R naught over 2 epsilon naught Z, sorry, that should be a negative 3 over 2, yeah? My mistake. I should put negative 3 over 2 there because we have negative half. Differentiate, we're going to have negative 3 over 2. So we're going to have a Z divided by R naught squared plus Z squared power to 3 over 2 in volt per meter. Okay, that should be our electric field, which is calculated at the point of 0, 0, Z. Yeah, given here previously is a potential there. So by using gradient method, yeah, by using gradient method in which we just differentiate with respect to Z, we are going to get the E field at that position. In which, if we can recall back, if we can refer to lecture 8, example 1, we are going to get the same electric field terms given in that slide. Okay, so that should be your electric field intensity. Any question for this example? So this example is just to show you how to calculate the electric field if you are given the potential V. So you have to be very careful on the use of gradient, yeah, in which you have to select the appropriate systems of coordinate. Okay. Any question for this example 2? No? Okay, there's no question. I just proceed with example 3, which will be the last example for today's lecture. Okay, using example 2 in lecture 8. So again, we are in the previous lecture 8. Obtain the E field intensity terms at the following location radius based on the previously obtained potential terms. Okay, so basically, this is similar to what we have done before. Okay, in which we have obtained previously in example 2 the potential at this location, R less than R naught and R bigger than R naught. So basically, the question is related to a spherical shell, radius of R naught, and we are given the charge of rho S. Okay, so what we did last time is that we calculate the potential, yeah, by using the equation of negative integrations of E dot dl from infinite to the point of interest, yeah, to the point of interest. For example, let's say at R naught, yeah, at R naught, what we did is that we integrate from infinite to the point of R naught. Okay, from infinite to the point of R naught, in which what we did is that we segregate the integration depending on the E field, because we know that for this particular case, there are two E field values. The first one is E1, which is inside the sphere, and another one is E2, which is outside the sphere. So you can, if you can recall that, yeah. Okay, so in this particular case, let's say at R naught, yeah, let's say here is at R naught, the potential calculated is V at R naught is equals to negative integration from infinite to r naught of E2 dot dl. Yeah, in which from infinite to r naught, we just pass through a single value of electric field, which is E2. That's why we just deal on the E2 terms there. Okay. Okay, this is what we have done previously in lecture 8, example 2. Okay, and we managed to find the potential V. Okay, so in this example, what is requested is that if we know the potential V at R naught, for example, yeah. So we need to find what is the E field at that particular position. So what we did is that we need to do the gradient, in which we need to find the negative of grad of V, okay, in which we need to evaluate the negative of a potential, which is this potential. Okay, so the gradient need to be based on spherical systems of coordinate. Okay, I don't want to do this in detail. I'm hoping that you can try to solve this first on your own. Yeah, just to show you that, just to test that you understand the method of gradient. So I believe that you have the value of V of R naught, right? So last time, if you can recall back, we have calculated 3 values. The first one is R naught over 2. Yeah, we have the V at R naught over 2. Then we have calculated the value of at R naught. We can find the V of R naught. And also at 2 R naught, where we have obtained the potential at 2 R naught. So we have 3 potential value at R naught over 2, at R naught, and 2 R naught. So what we have to do now, in this example, we have to prove that you can find the E field based on this given potential, where you have to use negative gradient of V. Okay, so I left this method of calculating the gradient for the potential of V, yeah, to you. So please solve this gradient potential to find the electric field intensity. Yeah. Right. So basically, the idea should be same like this. Should be the same. The difference will be on the use of this equation of gradient for this gradient for the spherical systems of coordinate, because you are dealing with a spherical system here. Yeah. Okay. So I need your help to solve this on your own. Yeah. Just do the gradient for me. Okay. I think that's all for today's lecture. Yeah. That's all for today's lecture. So for next week lecture on Tuesday, we're going to proceed with this calculation of energy in electrostatic field. Okay, I'm going to end the lecture earlier today, 12:30 already. Right, so no quiz today. Yeah, no quiz today. I'm expecting a quiz to be done next Tuesday. Yeah, next Tuesday, I'm hoping to have a quiz. I'm planning to have a quiz next Tuesday, a day before the test. So please make yourself ready. Quiz next Tuesday. Topics covered for the quiz, for the coming quiz will be on potential. Yeah, on potential. Okay.